Okay, so today my project partner, Krishan Kumar, and myself, Jaworski, will give you an overview of cooperative multi-agent reinforcement learning and an overview of its application to smart energy, the smart energy field. The rest of the presentation is just going to be divided into an introduction to multi-agent reinforcement learning, then an overview of the applications into smart grid, and the case study that will be for smart energy. So starting with multi-agent reinforcement learning. So as opposed to single agent RL, we can now see that we're interested in the modeling of the interaction of multiple agents with the environment. So the first consequence we can observe from this is that the environment that the agent is interacting with also is affected by how other agents act. So now effectively all agents, the actions of all the agents have an effect on the value function of all the other agents. So this is a generalized approach, and it's more akin to systems that we observe in the real world, and this is the reason why we're interested in characterizing ways to approach multi-agent systems because of their applications in, for example, autonomous robots coordination, social dynamics, traffic control, and energy markets participation. So as mentioned, one of the first things we lose when transitioning to multi-agent systems is environmental stationarity. So this is an assumption that allowed us to make many strong statements in the single agent RL setting that involve guaranteed convergence and guaranteed improvement of policies for algorithms. This is because we base all our theories on the Markov decision process, which involves just a space, action space, probability transitions, rewards, and discounting factors for a single agent interacting in the system that remains stationary throughout the process of interaction. But to deal with multi-agent systems, we have to switch now to what's called a generalized approach, a Markov game. So now we have to deal not only with the previous variables, but now also with a number of agents, with not only an action space for one agent, but the union of the actions set for all the agents, which is called the joint action space. And also a reward function that may change for each one of the agents. It's also worth mentioning the categories of multi-agent systems. For example, we can have cooperative multi-agent RL, which can be anything from cooperation of similar devices, or you can say members of a community trying to minimize their energy consumption. We can have competitive RL, which is any sort of, for example, the games we've seen in class, such as Go and chess. And we can have a mixed setting where we have team competitive games, as shown below. For the rest of the presentation, we're going to focus on the cooperative multi-agent RL applications, especially because it aligns well with the applications we're interested in energy systems, since now with all the smart grids, the relevance of smart grids and smart grid technology, we have a multitude of different energy systems trying to achieve a common reward, which is either some sort of energy balance or minimization of power consumption. So next, in cooperative RL, cooperative multi-agent RL, it's also worth mentioning that now all the agents are trying to maximize a common reward function. So now this equation we have on top is the Nash Q-learning update, which differs from the single agent Q-learning update in two main ways. Now we can see that the action space is not only from one agent, but it's the joint action space. And also at the end, we have this Nash equilibrium function, which just implies that now we're trying to look for a policy that will make all the agents unable to perform an action to make them better off than the rest of the agents. It's called the Nash equilibrium. Now, the main challenges for multi-agent reinforcement learning, as mentioned, are non-stationarity, but we also have partial observability because in the real system, we have no guarantees that all agents will be able to know the states and actions and rewards of all the other agents involved in the system. And scalability, because now every time we add an agent, it's not an extra agent, it's also an additional joint action space, which grows now exponentially. So this leads to other ways to approach this problem, such as should we allow the agents to communicate? Should we have a network? Should they be decentralized to address partial observability? Should they be centralized to address, for example, scalability, have a central controller that compiles all the information from the agents around it? And what if the agents are homogeneous or non-homogeneous? So for example, in energy systems, we can have a battery, heaters, as we are going to see later in our case study. So these are some of the considerations we have to have when dealing with cooperative multi-agent RL systems.
And now just broadly introducing RL for smarter energy systems. It's not a secret that ML and RL has become a very popular research topic. But if we look at keywords in research articles that relate to smart energy systems, we still see that there's a big gap between machine learning and reinforcement learning. And it does seem like this gap is just getting bigger. We do see a little bit of a takeoff in 2018. And I think a lot of people in the community are realizing what kind of an impact RL can have, especially on the smart grid of the future. And speaking of the smart grid of the future, there's going to be a lot of problems that future generations will have to deal with smart energy. Specifically, we can talk about control problems, we can talk about security problems, and as well, one of the main one is the dispatch problem, which relates to the incorporation of renewable energy sources in the smart grid. Because renewable energy sources are a variable energy resource, meaning that, for example, for solar energy, energy generations can be very high when it's very sunny outside and when it's like daytime outside. So it's like seasonal and daily variations. And if we look at the graph on the right here, the dispatch problem can be represented by this. The red line is demand and the blue line can be thought of as renewable energy generation. And there's going to be times when demand is much higher than renewable energy generation. And there's going to be times when there's going to be excess generation compared to demand. And so what people want to adopt as a solution is demand response in the term of energy storage solutions. For example, when generation is much higher, we can store this excess generation in batteries, or we can sell it back to the grid. And then we can use the energy that was stored in this period, or buy from the grid, which is more costly and worse for the environment. So these are some solutions that we're looking into.
A couple of the applications also related to smart energy are, for example, as one of I mentioned, the residential optimal energy scheduling. So you can have a community trying to achieve a net zero status with local generation and storage. So we need an agent, all the agents try to cooperate to achieve this net zero status. And also voltage regulation, which now with more distributed energy and variable energy, the variability of renewable resources in the grid, voltage regulation is quite a concern, and one that can be addressed also by multi-agent RL. And then also the management of just like electrical vehicle charging stations and the computing at the grid edge.
And now we'll go to our case study. For our case study, we used CityLearn, which is an open AI gym environment developed at a lab at the University of Texas, Austin. It's mainly developed for energy coordination and demand response of a group of buildings, which can be considered as a group of agents. This is specifically developed for multi-agent learning for demand response. What it is that there are about 9 buildings and 4 microgrids that can control energy storage systems in order to flatten the curve. And there's also 5 different climates. They give a bunch of weather data. They give a bunch of storage capacity data. The different types of storage we have are batteries, chilled and district hot water storage, heat pumps, electric heaters. There's PV arrays with different capacities for each building. So there's just a ton of different variables that we can play with. And because the problem is so big, we wanted to constrain the problem, or constrain the environment in order to test a couple of different multi-agent reinforcement learning models on. So when I talked about constraining the environment, the state space literally had like more than 20 different variables. We narrowed it down to 7: month, day, hour, non-shiftable load, solar generation, electrical storage, and net electrical consumption. And the action space had 4 different possible parameters, and we chose to go with electrical storage. Electrical storage can have a value ranging from -1 to 1, determining on if we want to fill up our battery or release the battery so that the buildings can use them. It's also important to mention that there is 5 years worth of data, so potentially you could run this model for a whole 5 years. And then I'll talk a little bit about QRTS, which is a MARL, a cooperative MARL algorithm that we tried to implement. It is a real-time swarm intelligence based on multi-agent Q learning. So it kind of takes single-agent Q learning and then adds on top of it. When I say add on top of it, I mean that there are Q matrices for each agent, and there's a Q swarm matrix that all of the agents have access to. So in each iteration, we first update the Q swarm matrix using this formula described above here. And we take the maximum of the Q values of the different agents in order to give more importance to outliers in updating Q swarm. And then once Q swarm is updated, we update the individual Q matrices, and we do this update with Q prime matrices. And then, but this update rule should look familiar from single agent Q learning. And then Q prime matrix is updated using Q and a linear combination of Q and Q swarm, which is parametrized by this beta parameter.
So we applied the QRTS, the described QRTS algorithm to a particular test setting with 2 buildings, 2 building attributes with only energy storage. We can see that the QRTS reaches and slightly beats the city-learn deadline baseline for these 2 buildings operations in the system we're considering. So this baseline is, we identified it as a saddle point for MARL, as we mentioned at the beginning of the presentation. The multi-agent RL systems lose all guarantees of convergence, and most of what's been proven for MARL algorithms have been empirical without any practical proof. So for these cases, in order to break this baseline and essentially like come above the saddle point, we suggest a more intelligent or efficient reward function design or a more efficient state space combination. So this is some of the results we got. So when we say we slightly beat the baseline, we say that we got our batteries to slightly smooth just the energy demand profile of 2 buildings, as we can see, for example, how some energy from the valleys here in blue was the original just net demand, and in orange is the demand, the new demand with the battery reaction. So we can see how the blue peaks are now lowered by the battery reaction, and blue valleys are heightened by battery reaction, which now effectively smooths out the profile of the community.
And so the second model we tested is MARLISA. This is multi-agent reinforcement learning with iterative action selection. And this is built on top of a soft actor-critic model. This model essentially uses deep neural networks with a soft actor-critic and regression in order to predict what the net electrical consumption of each building is going to be. So what this model does is it lines up each agent in a line, and then the first agent predicts, it chooses an action and then predicts what the net electrical consumption is going to be, and then gives that value to the second agent. And the second agent then chooses an action and predicts what its net electrical consumption is going to be, and then adds it to the previous agent's value and then sends that to the third agent. this kind of preserves security in a certain way. And then this process of predicting and aggregating goes all the way through the line and then loops back to the first agent. And so Marlissa kind of takes a really long time to train. So we trained Marlissa for one epoch and then compared it to QRTS trained for multiple epochs in the next slide. And here is a graph where we train the QRTS, train the agents using QRTS, and we see that it gets kind of close to the Marlissa range and then kind of behaves erratically after about episode 70. This is because the Q values are very sensitive and are sensitive to fluctuations because of the very large state and action spaces. Not all Q values are converging within the time frame that we're looking at, and just in general as well. And so these are the two models that we looked at.
Thank you very much for watching.